Okay guys, this is the 9th lecture, and after this there's an exam. I'll try to see if I can post a review lecture, but overall you should be able to download the slides and go over the material that we've covered. I will also post exams from previous year and solution to those, just like I did for 413. Okay, I'll do that as well, and please go through it, because sometimes I tend to repeat those problems. Sometimes I tend to take the homework problems and put them into the exams. So make sure you're going through the solved examples of the textbook, solved examples on the notes, the lecture notes on the CD or the website, and go through the old exams. These are very critical in order to get a best attempt. Okay, what we have been doing so far is designing the reactor, and we've been following this structure. So first we did the mole balance, then we looked at the rate law, then we looked at the stoichiometry, then we came back and combined this to design isothermal reactors. We took into effects for PBR over here, okay, and we discussed special reactors such as MBR, which is membrane reactor. Then we also looked at unsteady states like startup of a CSTR or a semi-batch reactor. Okay, so this is where we are going to stop and not go to heat effects right away. Now what I want to do in this lecture is go back to rate laws. Okay, remember I said that we are just brushing over rate law, just giving you a basic definition. Now I want to go back to rate laws, and I want to teach you guys as to how to take experimental data and then figure out a rate law. Senior lab, those who are taking senior lab, I think you'll have a PFR experiment with a plug flow reactor where you're, I think it's acetic acid, sodium acetate, formation of sodium acetate is what you study, and you measure that using conductivity, by seeing the conductivity. Okay, so this is where you'll use, or this is from, okay, today's lecture. But before we go into today's lecture, let's spend 2 minutes, just 2 minutes. So pick out a paper from your, book. And if you could tell me, I'm very serious about improving the teaching. As you can see, I'm trying to record lectures, adopt new technology, get them so you can review lectures at your own pace. I'm trying to improve my teaching skills as much as possible. And so what are 1 or 2 specific things that you see me doing to help you learn in this course? Because this course content has been developed over the last 4 or 5 years. Hasn't come, all of a sudden. So there are small changes that I've been making over the years. So what are 1 or 2 things that you really like compared to other courses? Okay, you've taken so many courses here. So what are 1 or 2 specific things that you like? Okay, and 1 or 2 specific things that hinder or interfere. Something, maybe it's a habit, saying, something like that. Okay, so if there's anything that you don't like, or that that interferes, please go ahead and put it down. See, I just said that. And what are practical suggestions would you give me that I can help improve this course? Okay, let's take 2 minutes to write these suggestions. Let's move forward. As I say, what we will do today is we'll look at how to take experimental data and extract rate law from it. Okay? So we'll be looking at 3 different kinds of methods. One is called an integral method. It is only applicable to batch reactors. It's very important to understand. That method is only applicable to batch reactors. Okay? Then is the differential method. The differential method, it's basically same set of equations. it depends on how you evaluate those set of equations. Using graphical method, or you use method of finite difference, or you use polynomial fit method. Okay, so in general the differential method is same, but it just depends on how you process the data. Okay, and the third method is the nonlinear regression, which you guys have done. 413, you guys remember we did nonlinear regression, like we calculated, we assume some values and then put a column of calculated values, then we calculated the error squared, and then we summed up the error squared, and we tried to minimize it by changing the assumed values. Remember? So that method is called method of nonlinear regression, okay, or nonlinear least square fit. Okay, so these basically we're going to go through. So what do you do when you're determining a rate law? Okay, these are the very basic steps. So the very first thing you do is you postulate a rate law. Okay, how do you postulate a rate law? You use what's called the power law model. Right? So minus RA is equal to K times CA raised to alpha, CB raised to beta. Something like this. Okay? So you postulate a power law model. And then the second step is you select a reactor type. So in senior laboratory, you will be doing an experiment where you have a PFR. So you're given that your reactor is a PFR, okay? And then you have to choose the corresponding mole balance. So you have to take that mole balance equation for PFR, okay? And then upon looking on the mole balance, you will figure out, okay, what do I need in order to fit this, mole balance equation? Are these terms given, or can I find it by experiment? Or how can I derive these from experimental values? Okay, and then you look for some simplifications, and then you do a data fitting, like maybe fit it to a polynomial or fit it to a line or something like equation of a line. Okay, and that's how you figure out the reaction rate constant, K, and the powers. Okay, alpha. Look at the very first kind of method. Okay, that's the integral method. Typically it's only applicable to a batch reactor. And so what is the mole balance for a batch reactor? What's mole balance for a batch reactor? It's dNA by dt is equal to RA times V. Okay, so number of moles of A are changing with respect to time. If you have a generalized reaction that gives A goes to products, then you can write it in terms of this equation. Next thing is the rate law. Okay, so rate law, for example, it's a single order. It follows the first order. Then we can write it as minus RA is equal to K times CA raised to CA raised to 1, but if it is alphath order, then CA raised to alpha, right? That's the power law model. Okay. Then comes stoichiometry. What does stoichiometry tell you? It helps you relate CA to what's in the mole balance? Na, right? So CA is equal to Na over V, right? Number of moles per volume. Now, V can be constant. For most of the batch reactor it is, because batch reactor is like it's an enclosed wall. And so, if you combine, you get this equation, minus dNA by dt is equal to K times CA raised to alpha. Okay? Now, can you write Na as, I'm sorry, where did the minus sign come from? Sorry about that. Can you write this Na as Ca times the volume, right? And so this can be converted into dCA by dt, but you have to multiply it by the volume. right? All I did was substitute Na equals Ca times V. Okay, so V is constant for most of the reactors, and so you can take it out, and this will be dCA by dt. Look, we can. So now let's go to what does the integral method state? The integral method. If you have a zeroth order, reaction, what does zeroth order mean? Meaning minus Ra is equal to K. That's it. Okay. So what does the mole balance become? dCA by dt is equal to Ra. Okay, and so it becomes minus K. And if you integrate this with the limit that at times equal to 0, Ca is equal to Ca naught, you'll get this equation that Ca is equal to Ca naught minus Kt. Right? You integrate, you bring time dt over here, so it is minus K dt. You integrate both sides, you get Ca is equal to integration constant plus Kt. Minus Kt. Right? That integration constant is evaluated by putting time is equal to 0. Ca is equal to Ca0. So integration constant becomes Ca0. And you get this equation. Okay? If you look at this, if you were to plot concentration versus time on the y-axis, what kind of a curve would you get? You're going to get a linear decrease. Okay? All right, let's go to the first order. Mm-hmm.
It's hard to read.
Okay, right. Oh, okay. At times equal to 0, I'm sorry, I think the projector has been moved. So at times equal to 0, Ca is equal to Ca naught, because initially you start with Ca naught more, and then when you integrate this one, you get Ca over here. You bring dt over here, you get minus K dt. You get time minus Kt plus some integration constant, right? After integration. So to evaluate the integration constant, you put in these limits. T is equal to 0, Ca is equal to Ca naught. So you put Ca naught over here, your integration constant becomes Ca naught. Okay? So you get almost a linear drop. Sorry about that. I'll keep that in mind in my next slides. Okay, let's say it's a first order. So you would have minus Ra is equal to K times Ca, right? So what would your mole balance or combined equation become? dCA by dt is equal to minus K times Ca. Okay? And so you would have dCA by Ca is equal to minus K dt. Go ahead and integrate this with the same limits. T is equal to 0, Ca is equal to Ca naught. You would get an equation that looks like ln Ca naught over Ca is equal to Kt. Okay. Because what is the integration of 1 over Ca? Natural log of A. And so if you evaluate that integration constant, you will get minus ln Ca naught. Okay? And then when you rearrange everything, you can get this form from there. So here, if you were to plot natural log of Ca naught over Ca versus time, what would you get? You would get a line passing through 0, and your slope over here is equal to the reaction rate constant. Again, the slope over in the 0th order graph is also equal to minus K. Okay. Let's say it is a second order reaction. Second order means minus RA is equal to K times CA squared. So in this case, you would have dCA by CA squared is equal to minus K dt. Okay, and then when you integrate, again, you just integrate, and you get this kind of a form: 1 minus CA minus 1 minus CA naught is equal to KT. So this is for the second order, right? What is the integration of 1 over CA square? It's minus 1 over CA, right? And so this is what you get. In this case, if we wanted to form an equation for a straight line, what are the terms we would have to plot? We'll have time on the x-axis. What would you plot on the y-axis? 1 over CA, right? So you would plot 1 over CA. And what would you have as your intercept and slope now? So let's say, in this case, it would look like this. Your intercept, what would that be? One over CA naught. And what would the K be? The slope. Oh, sorry, the slope would be the K, the reaction rate constant K. Okay. One important thing to note is that, look, the integral method, all it says is that take that data, concentration versus time data, and plot these three graphs. Whichever graph looks like a line, okay, whatever the graph resembles, if the graph resembles, what is supposed to be a zeroth order, then it's a zeroth order. If it resembles first order, it is a first order. If it resembles the second order, it is a second order. Okay. Now, how would you perform the same analysis if it was? So what we did earlier was for A gives products, right? What if you have an equation like this? How would you do the analysis? It's a critical thinking question. How would you do the analysis? How would you apply the integral method? Remember, what is the rate law for this equation? Like a general rate law, minus RA is equal to K times CA raised to alpha times CB raised to beta. I just heard a very nice find the limiting reactant. Okay. I think we can make something a limiting reactant here, because it's a choice, right? When doing reactions in the lab, we can make something a limiting reactant. So for example, if you wanted to make A as the limiting reactant, what would you have to do during the reaction? Huh?
I'll take A out.
You would have to hold the concentration term for B constant, right? If you wanted to make this into like a power law, you would have to hold CB constant, or the term with CB as constant, right? How would you do that experimentally?
Keep adding it as it goes out the same rate.
That's one way. What would be the other way? Just put a whole lot of B. Okay? So the change in the number of moles of B would be so less, you wouldn't see the change in concentration. I mean, it would be minuscule, small, compared to the change in A. Okay? So that's how it is done, is that you dump a lot of B in there and hold, to see how the concentration of A changes, right? And then you fit it to the integral method, and then you go back and, put a lot of A in there and see how the concentration of B changes. Okay? So it's the relative concentrations of A and B that you're changing to figure out K and alpha and beta. Okay? Okay, so this method only works if it is zeroth, first, or second order reaction. Okay, it does not work if it is 1.5th order or 2/3 order. It does not work. And so in those cases, you have to go back to the differential method of analysis or the nonlinear regression. Okay, so you have to go back to these methods. So let's go ahead and learn the differential method of analysis. For differential method of analysis, it's a set of equations that I used. So for example, you have again the equation A gives products. Okay, what would the mole balance equation be for a batch reactor? It would be dCA it would be minus dCA by dt times K Ca raised to alpha, or I can put the minus sign over here too. Okay. Let's say I take a natural log of this. Okay, I take a natural log of this. This would be ln dCA by dt is equal to, let me put the minus sign on this side, okay, and so it would look much more decent. So natural log of minus dCA by dt is equal to ln k plus alpha times ln Ca. The reason why I put the minus sign over here is because concentration of A is going to decrease, right? So your dCA by dt is going to be negative. So can you take a natural log of a negative term? Can you take a natural log of a negative term? No. You have to make it positive. That's why I put the minus sign over there. Okay? And so you get this equation. Now if you took your data, let's say you're given concentration versus time data, and you plot natural log of minus dCA by dt versus ln Ca, you would get a straight line, right? What would be the slope in this case? Natural log of k. So I'm sorry, the slope would be alpha, and this intercept would be natural log of k. Okay, let's go to generalized equations. A batch reactor. So now we can write down similarly generalized equations for a batch reactor, something like this: ln minus dCA by dt is equal to ln k plus, here I'm putting n, you could put alpha as well. So actually I'll just write alpha, ln Ca. Okay, for CSTR you would have an equation that looks like this: natural log of Ca naught minus Ca over tau is equal to ln k plus alpha times natural log of Ca. Okay, and for a PFR it would look like this: natural log of dx over dv is equal to natural log of k over fa naught plus alpha times natural log of Ca naught times 1 minus x. Okay. Here are the main three equations that you have to kind of use every time. Again, just a clarification. This is chapter number 5 material, and it's not covered on the exam. Okay, so whatever was covered in the last lecture and up to the last lecture is what's on the exam. This is for exam number 2. So these are the 3 equations that we apply again and again. What we will do today is look at how to apply the equation for a PFR, which looks a little bit more complex. I think if I demonstrate one for PFR, you should be able to figure out how to apply for CSTR or batch reactor. So the differential method, okay, we saw the 3 equations. Now, there are 3 methods based on how you calculate the differential term. So in case of a PFR, you have this dx over dv. Okay. In case of the batch reactor, I think it is dCA over dt. So how do you calculate these differential terms? Okay. Based on that, there are 3 methods: graphical method, finite difference method, and the polynomial method. Okay. The graphical method, what does it say? It says, let's say you're given concentration versus volume data, then you calculate delta CA over delta V. Okay. If you're given conversion versus volume data, you calculate delta X over delta V. Okay. What you do is you plot this data as a histogram versus the volume. Okay. And then from that graph, we'll learn how to calculate dCA by dt, okay, from a delta CA by delta V histogram, or dx by dV from a delta X by delta V histogram, okay. From this calculation, then you go ahead and fit this ln dCA by dt. So you take the natural log of dCA by dV, or in case of dx by dv, you take a natural log of that and plot it against ln CA, or for a PFR, you plot it against ln 1 minus x. Okay. When you plot this, basically, you get a graph looking like this. Your intercept will help you calculate k, and your slope will help you calculate alpha. Okay, that's what the graphical method says. Let's do an example. Do you have a textbook? Okay. Alan, can you read this particular problem statement, P5-4? It's an unsolved problem in the back of your textbook, and we're going to go through that. Can you read that problem?
When arterial blood enters a tissue capillary, it exchanges oxygen and carbon dioxide with environment as shown in this diagram. I can't talk today. The kinetics of this deoxygenation of hemoglobin in blood was studied with the aid of a tubular reactor by Nakamura and Staub. Although this is a reversible reaction, measurements were made in the initial phases of the decomposition so that the reverse reaction can be neglected. Consider a system similar to the one used by Nakamura and Staub. The solution enters a tubular reactor, 0.158 centimeters in diameter, that has oxygen electrodes placed at 5 centimole intervals down the tube. The solution flow rate into the reactor is 19.6 centimeters cubed per second, with Ca naught equals 2.33 times 10 to the negative 6 mole centimeters cubed. Using the method of differential analysis of rate data, determine the reaction order and record specific reaction rate constant K1 for the deoxygenation of hemoglobin. Repeat using regression.
Okay. Thank you so much, Alan. So what this problem is stating is that every time oxygen combines and gets released from the hemoglobin, those kinetics are reversible kinetics. Okay, and the equation looks something like this, and you can carry this out in the lab. So when you carry this experiment out, for example, if you have oxygen attached to hemoglobin, okay, let's say it goes to the tissue. Okay, goes from the lungs to the tissue, and at the tissue, it basically decomposes to hemoglobin and oxygen. It gives the oxygen to the cells. Okay. Now in the lungs, again, it goes back. It's a backward kinetics, right? So you're told that this experiment, you can neglect this K minus 1 if you do this experiment and measure this decomposition like initially. Okay, so you wouldn't have formed so much oxygen to reverse the reaction fast enough. You're given that the concentration is this much, okay, and you're given the volumetric flow rate. So from this you can calculate your FA naught, and you're given that the diameter of the tube is 0.158 centimeter. Look at the data. The data shows electrode position, okay. The spacing between two electrodes is 5 centimeters. Is that correct? Yep. So you have first electrode position at, let's say this is the tube. Your first electrode position is here, right? Second over here. So let's say 1, 2, 3, 4, 5, so and so, and the interval between two electrodes is 5 centimeters. That's what it says. Okay. So now, how do we go ahead and calculate using, the rate date, like calculate the reaction rate order and the K1 or K using this data? Okay. See, what you're also given is the percentage decomposition of HbO2. What is percentage decomposition? What do you think that is? It's just conversion given in terms of percentage. Okay? It's just conversion given in terms of percentage. Okay, so let's go ahead and try to solve this and show. I want to show you how to use the graphical method to calculate. Okay, so what does the differential method state? The differential method states that minus RA is equal to K times Ca raised to alpha, okay? And for a PFR, the equation that we just looked at, it follows something like this. Fa naught times dx over dv is equal to K times Ca raised to Ca naught raised to alpha times 1 minus x raised to alpha. Okay, and the differential form is natural log of dx over dv is equal to natural log of k over Fa naught plus alpha times natural log of Ca naught times 1 minus x. So what we need to do is we need to calculate dx over dv and this term Ca naught times 1 minus x, take natural log of those two, okay, and plot them, right? If we plot them on a graph, so ln dx over dv, and here you have ln Ca naught times 1 minus x, you would get from the slope alpha, and from the intercept you would get natural log of k over Fa naught. Okay, I'm sorry if it's not visible, but okay, that's exactly what we are trying to do. And so we're going to evaluate dx over dv using the graphical method. So the graphical method is like, where is it negative? No, dx over dv is not negative because conversion increases. You don't put a negative sign over there. It's the concentration is negative. Okay? So the table that you're given, so for example, you have electrode position, right? And then you have percentage decomposition given to you. Can you make one more row below it. Like let's say you start writing in your notebooks. Can you make one more row below it? Can you just write this percentage decomposition into fraction? So for example, if the percentage decomposition is 0 here, the fraction of it is 0. If the percentage decomposition is 1.93, can you write it as 0.0193? Okay, and so and so. Can you take care of writing that, please? So you have your textbooks in front of you, right? So go ahead and take this table, copy it down in your, and feel free to group, okay? Feel free to group. So if you don't have textbook, just peek into somebody's with permission. Now, so go ahead and put this third row, which is the conversion, okay? And after you're done putting the third row, let's put a fourth row which calculates the volume. How would you calculate the volume? If you know your diameter of the tube is, I believe it's 0.158. So it's 0.158 centimeters. And so what would be the volume at the first position? 0, because it's right at the beginning. Okay. For the second, what would be the volume? V is equal to pi by 4 d square times the spacing, right? L between two electrodes. So pi by 4 d square, that's 0.158 squared, okay, times the length. What's the interval between two electrodes? That's 5 centimeters. If you calculate this, you get roughly about 0.1. centimeter cube. Okay, you get about 0.1 centimeter cube, and hence the volume over here for the second position, that would be 0.1. Okay, roughly about 0.1. I think it's 0.09 something if you do an accurate calculation. Okay, what would be the position for what would be the volume for third electrode? 0.2. Okay, fourth electrode 0.3, and so and so. Go ahead, please go ahead and write down this, complete this fourth line. Okay. Okay, once you're done, is you're going to calculate, so after x, let's say you calculate V. Now we want to calculate delta x, that is the change in conversion. Okay, so let's say this is 0, I'm sorry, conversion is 0.0193, 0.0382, and so and so and so. And your volumes are 0, 0.1, 0.2. I believe this one comes out to be like 0.29, because there's this plus minus, like it's actually 0.09 something you're adding. So for the third electrode, it comes out to be roughly about 0.29 or so. Okay. Okay. Then you calculate delta x. Okay. We're not going to put any value in the first cell. But in the second cell, we're going to take a difference of these two. So we're going to say 0.0193 minus 0. Okay, so that will be 0.0193. Over here in this cell, we're going to take a difference of these two values. So it would be 0.0382 minus 0.0193. So whatever that value comes out to be. And so and so. If you do it here, you're doing your homework problem. You can do this in Excel as well. You know, Excel, you just drag the cell and you should be able to kind of do it faster. Okay. So after you calculate delta x, then you want to calculate delta v. Okay. Delta v for the first cell, it's going to be, we cannot put any value. But for the second cell, it's going to be roughly about 0.1. Second cell is roughly going to be about, 0.1 as well, because the volume delta v is fixed, right? Roughly about 0.1, so and so. It's a fix. It's a constant interval of 5 centimeters, and so your delta v between two electrodes is the same. And then we calculate delta x over delta v. Okay. Then you calculate delta x over delta v. So the delta x over delta v is basically this value divided by this value. So you would get 0.0193 divided by 0.1. Okay. For this cell, it would be this value, which is 0.0382 minus 0.0193. Divide by 0.1. Okay, so it'll be this value divide by 0.1, and that will go here. Feel free to run it on your calculators. That's why I'm going very, very slow. Okay, feel free to run it on your calculators. This is exactly what the homework problem is. So you calculate delta x over delta v. Now in the graphical method, if you go back to the algorithm, okay, the algorithm says you have to plot a histogram. Okay, histogram of delta x over delta v versus v. Okay, you have to plot a histogram. Everybody know what a histogram is? It's like bar charts. Something like, you know, a column chart. Okay. When I did this on an Excel sheet, this is the kind of column graph that I got. Okay. Delta x over delta v versus volume. This is the kind of column graph that I got. Then, what you need to do is, in order to calculate dx over dv from here, from this graph, what you have to do is you have to draw a line. Actually, if you are doing on a graph, you actually try to draw a line that, you know, touches the center point in such a way that this area right here is equal to this area right here. Okay, should I change the colors? See, I'm going to do it on the other. This area right here is equal to this area right here. You try to draw a line going through all of these. Okay. What I did in Excel was I just click the data, give it a right click, said fit it to a trend line, and made that trend line a polynomial. Okay. You have to see which polynomial fits the best. So it's a trial and error. You have to go, second order, third order, fourth order, fifth order, first order also. And then I got this polynomial that looks like, okay, y is equal to so and so and so. Okay, this y is actually dx over dv. Okay, that y is actually dx over dv value. So for example, if you wanted to find let's say graphically you wanted to find dx over dv for volume is equal to 0.05, you would look up where does this line cut this column, and then look up that value. Actually, I'm sorry, it's the other way. Wherever it cuts, you look up the volume, and so you now have dx over dv versus volume. Okay. Anyway, so this is how you do it in Excel, is that you fit it to a polynomial, and then that polynomial y will give you dx over dv. Okay, so in the table, after you calculate delta x over delta v, right, the next row is going to be for dx over dv. Okay. The next row is going to be dx over dv. So for 0, what is the value for dx over dv in this polynomial? Your x over here in this polynomial is v, volume. Okay? And so if your volume goes to 0, right? Volume is, this is volume, first cell volume is 0. Next one is like 0.1, then 0.2, something, so and so and so. So for your first cell, for dx over dv, what is the value for 0? What is the value for dx over dv? When volume goes to 0, it's 0.2022. Right? Then your volume goes to 0.1. You substitute 0.1 in here in this polynomial. You get another dx over dv value. Okay? And so you use this polynomial to calculate dx over dv. You substitute x is equal to v from these cells. Okay? That's how you calculate dx over dv. Now what is the next thing? Again, we did this graphical method to actually calculate dx over dv. Now we go back to our differential method and we say, yeah, we have to plot ln dx over dv versus ln ca naught times 1 minus x. When we plot this, it's a straight line. Slope gives us the reaction order, and the intercept gives me the k over fa naught. Right? That's what we did in the last slide. So that's exactly what you do. You calculate natural log of dx over dv. Okay. And then the next row you calculate ln, this value, ca naught times 1 minus x. I'm sorry, it's a little bit messy. Now ca naught is given to you, right? Its value is about 2.33 times 10 raised to minus 6 moles per centimeter cube. All you're doing is changing conversion, so you have to use the right x value. Okay, so your x value changes. Okay, x value changes. Now if you plot this one, so when I did that, I got a graph like this. Look, this is ln CA naught times 1 minus x. This is ln dx over dv. I got a linear graph that looks like this. Again, ln CA naught times 1 minus x was negative, okay, and ln dx over dv was negative. Why is it negative? Because natural log of small numbers is negative, okay. Natural log of something 10 raised to minus 6 is going to be a negative value, okay. You get a straight line, and I just right click those points and fit it to a trend line, an equation to of a line, okay, and it gave me an equation that looks like this. Now what did I say about the intercept? Intercept is natural log of k over fa naught, and that is 10.93, and the slope is equal to the reaction order is equal to 0.9682. So that's roughly equal to 1. It's a first order reaction roughly, okay. Here you know your FA naught. I believe FA naught is equal to 45.67 times 10 raised to minus 6 moles per second. And so if you calculate, you will see K comes out to be 2.55 I believe the units are second inverse. Okay, so that's the graphical method. Now let's say, this is tedious, graphing things, getting a graph. More simpler method, it's called the finite difference method. This is the method typically you will apply on the exams, and this method you can do very quickly by hand. What does the finite difference method say? Finite difference method says is that you can calculate that dCA by dV, or in case of batch reactor, or dx by dV in case of a PFR reactor, using numerical formulas, okay. And those numerical formulas are something like this. For example, if it is the first point in that table, then you have to use this formula, dCA by dt is equal to minus 3 CA naught, okay, meaning CA naught, meaning for the first point, okay, times 4 CA1, that is the second point, minus CA2, which is the third point, divide by 2 times delta t. So this is the dCA by dt for the first point, okay. All right, then if you're calculating for intermediate points, okay, it is not the first point or the last point, then you use this formula, dCA by dt is equal to CA2 minus CA naught divided by 2 times delta t, okay. So let's say you're calculating dCA by dt for the second point, then you have to take CA2, which is the value for concentration for third point, minus the value for concentration for the first point, divided by 2 times delta t, okay. And if it is the last point, okay, in that table, then now this is for concentration, okay. You can similarly write for conversion as well. So dCA by dt you calculate as Ca raised to n minus 2, okay, minus 4 times Ca raised to Ca n minus 1 plus 3 times Ca n divided by 2 times delta t. So dCA dt for the last point is calculated based on concentration value for the last point, as well as the point before, as well as the 2 points before, okay. You use 3 values to calculate this. So once you form and calculate this dCA by dt, same thing, you go back to the method of differential analysis. you calculate natural logs and you plot it against the correct term, and then you get the reaction order from the slope of this fit and the value of k from the intercept. Again, so let's go back to our problem. Okay, we were talking about this hemoglobin problem. So here we have conversion x given, okay, and the volume given. We have to calculate dx over dv. Dx over dv. So we have to go back to our formula. So for first point, okay, the formula says minus 3 times Ca naught plus 4 times Ca1 minus Ca2 over 2 times delta V. So instead of time, we would have a differential of volume. Okay. Basically, those formulas were just generic formulas. I just used it for concentration versus time data. You can change it to something like this. So instead of, you would have to replace these concentration terms with x values, right? Because you're calculating x. So it will be x instead of concentration. All I did was change that formula that I gave you for concentration and time to one for conversion and volume. Okay. So what is xa naught in this case, or I should say x naught instead. I'll just remove that a. Okay. Okay. So what is x naught over here? It's 0. Okay. What is x1? It's the next value. I'm sorry, 0.2. And then 0.04 becomes x2. Okay. And delta V, you will note that this is constant. Delta V is constant. It's 0.1 in this case, 0.1 centimeter cube. Okay. You see how to calculate this? So it will be minus 3 times 0.0193 plus 4 times x1, that's about 0.0382 minus 0.0568 divided by 2 times 0.1. Sorry? I'm sorry. Yes, thank you for catching my mistake. This is 0, this is 0.0193, this is right, and then this is 0.0382. Thank you for catching my mistake. That's my mistake. So that is for first point. And for all the intermediate points, so let's say we do the second point. Right, I just rounded it up here because my Excel rounded it to 2 decimal places. For the second point, dx over dv, how would I calculate that? Well, the formula says, Ca2 minus Ca0 over 2 times delta T. So I'm going to use the eraser function here. I'm going to change Ca to x and T to V. Okay, so this would be x and this would be V, right? And so you can calculate this as, for the second point it would be 0.0382 minus 0 divided by 2 times 0.1. Okay, that's for the second point. For the third point, your dx over dv will be x3 minus x1 over 2 times delta v. So that would be 0.0568 minus 0.0193 divided by 2 times 0.1. Okay, so what I did was this point minus this point divided by 2 times delta v. Okay, and so you can calculate. And for the last point, you use these values for x. You use this value, and this value. Okay, so that's how you do is you fit it to a trend line, and you get you take natural log and get the conversion. Okay, I'll quickly go over the polynomial method. Polynomial method says just fit the data as it is to a polynomial, differentiate it. Okay, here's our example. All I did was in Polymath, you can do this in Excel as well, just fit that conversion in terms of some polynomial. For here I wrote z, you can write v as well, okay, in terms of v. Great. Now can you do a differential of this polynomial? Yeah, I know, because differential of a constant is 0. For a1 times z, it would be a1, right? So then you have an equation for dx over dv. Okay, so that is the polynomial method. And then again, nonlinear regression, and then you get the value from there. I mean, not nonlinear regression, sorry. You fit it to a straight line, and you get the value. So look at the value of alpha here. Look at the value for natural log of fa naught over minus, natural log of k over fa naught is this. You see, basically it's just different methods of analysis. Okay, we're going to stop here.